Hello everyone, I hope you have been doing well. I just want to emphasize that graphs play a very important role in science, especially physics. Therefore, I need you to make sure that you watch all of the videos and write down your own personal notes until you have a complete understanding of graphs. The reason for this is that it will be coming in exercises, experiments, tests, and examinations. And of course, if you have any questions, always feel free to ask. Looking at this graph, period squared is plotted against length. Then, looking closely at the points, we notice that they do not form a perfect straight line, and this could be due to systematic errors or random errors. Hence, a best fit line is done to find the trend of the data and reduce the effects of errors on your calculations. Now, let's move on to some tips to remember when doing a best fit line. First, trying to force the line through the origin or particular points for this graph resulted in a red line which did not go through most or get close to many of the points plotted. Remember, it does not need to go through the origin. The aim is to follow the trend of the points. Second, having too many points on one side of the line versus the other. For this graph, this resulted in a red line, which was not a well-balanced best fit line. So the aim is to try to have the same amount of points on both sides. Third, the line of best fit must reflect the trend of majority of the points. For this graph, the green line was close to most of the points with only one outlier that does not follow majority of the points. So the aim is to get as close to or through as many points as possible. With practice, once you take your time to carefully move your long ruler right and left, you will eventually be able to do best fit lines easily. A website has been linked in the description which you can use for more practice. In the previous video, when we were plotting graphs, we used a formula to get the scale, which would take up as much space as possible on the graph paper. This scale determined the centimeter blocks. Now, our aim is to determine the value of the small lines, which you will see in between the centimeter blocks. This can be done by using this formula. Looking at an example, we observe two numbers, 0 and 10, with a unit of centimeters in the top left. The first number we get to is 0 and the second number is 10. And it takes 10 lines to get from 0 to 10, making sure I did not start counting at the same line as the first number. Now, when we substitute all this information we just found into the formula, we get 1 centimeter per line. Something to note is that this example represented a ruler. However, these steps can apply to any instrument such as a graduated cylinder or triple beam balance. Example, which uses a section of graph paper, we will apply the formula given on the previous slide. When using the formula, any two numbers can be chosen, and for the x-axis, the possibilities are 0 and 0.05, 0 and 0.1, and 0.1 and 0.15. While for the y-axis, it is 0 and 0.2, 0 and 0.4, and 0.4 and 0.6. For the calculation, we will choose 0 and 0.1, which has 10 lines from the first to second number on the x-axis, and 0.4 and 0.6, which has 5 lines from the first to second number on the y-axis. Substituting this information into the formula, we get 0.01 per line for the x-axis. So let's check our calculations were correct by counting with the value for the x-axis. For the x-axis, starting at 0, it goes 0, 0.01, 0.02, 0.03, 0.04, and 0.05. This matches back the number seen on the graph. Now, substituting the information for the y-axis, we get 0.04 per line for the y-axis. So let's check our calculations were correct by counting for the y-axis. For the y-axis, starting at 0, it goes 0, 0.04, 0.08, 0.12, 0.16, and 0.2, which also matches the number seen on the graph. Doing these checks lets you know that what you have done for your calculations were done correctly. Using the value for each line which we just calculated, we will plot a point of 0.13, 0.5. To do this, one of the first steps is to establish where your x value can lie based on the value seen at the centimeter block. 0.13 must lie between 0.1 and 0.15. And counting using the per line value, we get 0.11, 0.12, 0.13, and 0.14. And we know that the x value is 0.13, so it lies directly on the line. For the y-axis, we are plotting 0.5, so it must lie in between 0.4 and 0.6. So counting using the per line value for the y-axis, we get 0.44, 0.48, 0.52, and 0.56. But this time, the value of 0.5 is not so obvious. So looking closely, we know it will lie in between 0.48 and 0.52. Plus, 0.5 happens to be about halfway between these two values, so we know it must lie midway in the space, and we plot the point. Of course, if we have a value that is closer to 0.48 or 0.52, this would affect how far up or down you move that point in the space. Please note that when you are plotting your point, you are not to show all of these counting lines as seen in this video. This is because this is only shown on this graph for demonstrating purposes only, so that you can see. Thanks for watching this video. The next video will be part 2 of this video actually, which focuses more on gradient.